Welcome to our class on stoichiometry. This time we'll be looking at calculations involving stoichiometry. On the board we are having three questions, and these three questions will guide us to understanding how we can attempt questions on calculations involving stoichiometry. Now, these questions I will give you tips on how you can attempt questions on stoichiometry and you won't be having issues. So you have to pay attention. Now, there is a formula that I'll be dropping, or a code that I'll be dropping, that will be of help to students that are actually having issues in calculations involving stoichiometry. And I call it the REMA code. The REMA code. Now, this REMA code tends to expose some certain stuff about stoichiometry. Now, before you can attempt stoichiometry questions, you must know how to balance reactions. It is of utmost relevance in stoichiometry. Many students they have issues with stoichiometry because they do not know how to balance reactions, or they do not even know how to represent reactions. So that's even the reason why the fundamentals of chemistry is of utmost relevance here. All right. So if you are able to balance reactions, then you can work with the balanced reaction and you are rest assured to having your correct answer. What are the three stages or steps that you need to pass through in order to obtaining the correct answer and solving with ease? The first step is that you isolate the relevant substances from the reaction. After you have isolated, then you convert the language of the equation to the language of the question. I will explain all this. And then lastly, you will now ask yourself the question that was actually asked from the statement. All right? So you won't understand this now until we start by looking at questions. So let's start by looking at questions. The first question is, what is the mass of calcium oxide produced by the decomposition of 30 grams of limestone? Now, we are told to calculate the mass of calcium oxide that will be produced by the decomposition of 30 grams of limestone. The question is, what is limestone? Solution to question 1. Now, limestone is having a formula CaCO3, which is calcium carbonate, or you can go by the IUPAC name, calcium trioxocarbonate 4. Now, this is actually an unstable salt compound to heat, in that when heat is applied to this, it tends to decompose, releasing CO2 gas as well as calcium oxide. You can actually visit my video series on salts, where I explain some certain stuff about salts, then you begin to understand better. Now, for this CaCO3, it is an unstable trioxocarbonate. When heat is applied to this compound, it produces CaO plus CO2. So you see the reason why in stoichiometry you have to know how to represent reactions and then balance. Now, this is the limestone producing quicklime, being calcium oxide, and releasing the gas CO2. Let's confirm that the reaction is balanced. Now we are having one calcium, one carbon, and 3 oxygen, 1 oxygen plus 2, that's 3. So it's balanced. Always in stoichiometry, you represent each of the substances with the mole ratios of, in this case, this is 1 mole. So it means the language of the equation always speaks moles. Then this one is 1 mole, meaning no number before it, so it's assumed to be 1. Then while this one is also 1 mole. All right? So you see, the language of the equation always speaks mole. Then the next, we are told that what is the mass of calcium oxide produced by the decomposition of 30 grams of limestone. We are aware that this is our limestone and this is our calcium oxide. So following that my basic principle that isolate, convert, and ask. Let's go. For the isolate, it means that we have to isolate the relevant components in this reaction. Of course, how do we get the relevant components? It is what is stated in the question. Now, we are told what is the mass of calcium oxide, meaning that calcium oxide is a very important substance that we need in this equation. Then let's move on. Produced by the decomposition of 30 grams of limestone, meaning also limestone is still very important. So the only two important substances in this reaction happens to be limestone and calcium oxide. So we can isolate them. That becomes CaCO3, then CaO, 1 mole and 1 mole. We have just extracted the relevant parts of that equation. That's isolation first. Then the second, we will now convert. What are we converting? We are converting the language of the equation to the language of the question. Language of equation to language of question. Remember, the language of the equation always speaks mole. Now, looking at the language of the question, they said, what is the mass of calcium oxide? Meaning, we are interested in obtaining the mass of calcium oxide. So what does that mean? It means we have to convert the mole, this 1 mole from the equation of calcium oxide to mass. And don't forget, in our previous video, the introduction to stoichiometry, I said that molar mass is actually the mass of 1 mole of a substance. And usually, the mass of 1 mole of any substance can be ascertained by working with the relative atomic mass of each of the elements that make up the substance. Alright, so it means that 1 mole of calcium oxide will be equivalent to the value in grams of this. And how can you get it? Let's convert this to grams. So converting 1 mole of this to grams, it means we have to work with the relative atomic masses that was given in the question in order to obtain the mass in gram. And that becomes what? Calcium being 40 plus, then oxygen being 16. So when you sum up, since it's 1 mole, then it becomes 40 plus 16, that's 56 gram. So it means that in 1 mole of CaO is equivalent to 56 grams of CaO. Are you with me now? So then, looking at this calcium carbonate, which is the limestone, let's see the language of the limestone. It's still in grams, because then they said by the decomposition of 30G, which is 30 grams of limestone. So it means we still have to convert this to what? To the language of the question, being that we want to convert the mole to what? To mass. And that becomes 1 mole of this would now be 40, which is calcium, plus 12, then plus oxygen is 16, so 16 times 3. So that becomes 40 plus 12 plus, then when you do this, it becomes 48. So when you sum up everything, we need the help of our calculator. That becomes 40 plus 12 plus 48. That gives us 100. So this is 100 grams. So we have just converted the language of the equation to the language of the question. Then let's now ask ourselves the question, which is the last. We've done this, so let's ask ourselves the question. So the question is, what is the mass of calcium oxide? So we don't know the mass of calcium oxide that will be produced by decomposition of 30 grams of limestone, meaning 30 grams of limestone. So what it means is that when 100 grams of limestone decomposes, it produces 56 grams of calcium oxide. So they are now asking us, what grams of calcium oxide will be produced when 30 grams of limestone is decomposed? So we can use the normal linear format. If 100 gives this one, then 30 would give this unknown. So what do? We'll now cross multiply. So when you cross multiply from here, then it becomes what? 100 times x is equal to 30 times 56. And when we do that, it becomes x equal to 30 times 56 over 100. That's by division by this 100. And when we do that, we are going to be having 30 times 56. That becomes 1000 1680 over 100. And when we divide that, of course, we are going to be having 16.8. So 16.8 grams. So it therefore means that our answer is 16.8 grams, in that 100 grams will release this. The decomposition of 100 grams will produce this, while the decomposition of 30 grams will give us 16.8 grams. So that's for question 1. Then let's look at the second question. Looking at question 2, now we are given that what mass of sodium hydroxide is required to produce 3.4 grams of ammonia on reaction with ammonium chloride. Now, let's carry out the reaction. Like I said, one very important thing in stoichiometry is that you are able to represent the reaction. Now, we are told what mass of sodium hydroxide is required to produce 3.4 grams of ammonia on reaction with ammonium chloride. So it means there's a reaction between sodium hydroxide and ammonium chloride. Listen attentively. In stoichiometry, you have to understand the questions very well before you can start your calculations. Now, there's a reaction between sodium hydroxide and ammonium chloride. So that becomes ammonium chloride, which is NH4Cl plus, then we are giving sodium hydroxide. When we carry out this reaction, it becomes sodium chloride plus water, then plus ammonia. How did I get to know these products? It's because I'm acquainted with my bases, chemical reactions of bases. You can visit my video lessons on acids, bases, salts, and water, especially on bases. Chemical reactions of bases is that one of them, bases tend to react with ammonium salts to liberate ammonia gas. So you have this kind of reaction. So let's see whether the reaction is balanced. One nitrogen, then 5 hydrogens, 4 plus 1, 5, 3 plus 2, that's 5. Then chlorine 1, 1, sodium 1, 1, oxygen 1, 1, then everything is balanced. All right. So we are told what mass of sodium hydroxide. So let's start with that code. Remember the code: isolate, then you convert, then you ask. So don't forget this. So now looking at the question, let's see the relevant components of the question. What mass of sodium hydroxide, meaning this one is still very relevant, is required to produce 3.4 grams of ammonia? So you see it now, to produce 3.4 grams of ammonia on reaction with ammonium chloride. So what it means is that the ones that you are being given values for are the relevant ones. Or probably you are giving value of one, then you are expected to find the value of another. Those are the relevant ones. So of course, we are expected to find the value of sodium hydroxide while we are giving a value for ammonia. So you just isolate the relevant ones. What are the relevant ones? This and this, which is sodium hydroxide and ammonia. So you bring them out. NaOH to give NH3. And don't forget, remember that in terms of the stoichiometric ratios, this one is 1 mole. Remember I said the language of the equation always speaks mole. And while this one is 1 mole, this is 1 mole, 1 mole, and 1 mole. All right? So this still remains 1 mole to 1 mole. All right? So now, what we have already isolated, that's the first. Then now, the next is to convert. And remember, conversion is you are changing the language of the equation to the language of the question. So let's follow. What mass? Meaning the mass of sodium hydroxide is of utmost relevance here. So we are not interested in the mole of sodium hydroxide. So it means we have to convert this 1 mole of sodium hydroxide to mass so that we tally. And of course, converting this one is very easy now. We are given the relative atomic mass of each of the elements. So for sodium is 23. So 23 in this compound plus oxygen. Oxygen is 16. So 16 plus hydrogen. Hydrogen is 1. So when you sum up everything here, 23 plus 16 plus 1, 23 plus 16 plus 1, that becomes 40. So we are left with 40 grams. We've just converted. Then in the case of this one, let's observe what language are we having in the question. Now, it's required to produce 3.4 grams, meaning it's still in mass, of ammonia So it still means that we still need to convert this mole to mass. And of course, doing that, we are giving our nitrogen. Nitrogen is given to be 14. So 14 plus hydrogen being 1, it becomes, since there is a 3 subscript, that becomes 3 times 1. That becomes 14 plus 3. And 14 plus 3 is what? 17 grams. So 40 grams to 17 grams. Then now, we've been able to convert the language of the equation to the language of the question. The next is to now ask yourself the question. And what's the question? They said, what mass of sodium hydroxide? So we don't know the mass of sodium hydroxide. That will be required to produce 3.4 grams of ammonia. So we know the grams of ammonia that will be produced. Then we can easily get it because we are aware that this one can produce this one, meaning 40 grams can give 17 grams. So what can the unknown give of 3.4 grams? So what's not the unknown here in this case? So you just simply cross multiply, just like the previous question. So when you do that, it becomes 17 times x, which is equal to 40 times 3.4. And by doing that, x becomes 40 times 3.4 over 17. And when we do that, 40 times 3.4 divided by 17. Of course, that gives us 8. So we are left with 8 grams. So our answer is 8. All right. So that's just what you need to do about this question. Then let's look at the third question. Looking at the third question, number 3. We are given what volume of carbon dioxide gas is produced after burning 1.1 grams of propane in excess supply of oxygen at standard temperature and pressure. Now looking at this kind of question is different from the previous two. Why? Because in this question you were given mass and you were expected to find volume. So this is a volume mass relationship or mass volume relationship. All right. Now we need to understand something, a very good concept in stoichiometry. And what's that concept? Now, one mole of any gas occupies 22.4 dm cube of volume. All right, so don't forget that 1 mole of any gas occupies 22.4 dm cube of volume at STP. Yes, that's even the completion, meaning at standard temperature and pressure. All right, so 1 mole of any gas, meaning 1 mole of nitrogen gas, oxygen gas, CO2 gas, H2 gas, all of them, 1 mole occupies 22.4 dm cube of volume at STP. Remember that this 22.4 dm cube can also be replaced with liters, so it's equivalent to 22.4 liters. And again, you can use another unit for it. It becomes 22,400 cm cube. Yes, that's equivalent to that of 22.4 dm cube. All right, so don't forget that 1 mole of any gas occupies 22.4 dm cube of volume at STP. So let's get down to this question. Now, what volume of carbon dioxide gas is produced after burning 1.1 gram of propane in excess supply of oxygen at standard temperature and pressure? Now, propane is an organic compound. It falls under a member of alkanes, that's under organic chemistry. And whenever you combust any organic compound, complete combustion, meaning excess supply of oxygen, it releases CO2 and H2O. And of course, propane happens to be having a formula. The formula of propane is C3H8, and it happens to be a gas too. So propane being C3H8 is combusted in oxygen to release CO2 plus H2O. That's excess supply of oxygen to cause the complete combustion. So balancing this reaction, how many carbons here? 3. So we have to make here 3. Then how many hydrogens? 8. Then here is 2. What do you multiply by 2 to get 8? Of course, 4. So that becomes 4 times 2, 8. Then oxygen here is 2. But here is what? 3 times 2, 6. And here is 4. So 6 plus 4 is 10. So what do you multiply by 2 to get 10 is what? 5. So balance the reaction. So the reaction is balanced now. All right. So now remember our principle: isolate, convert, and ask. So let's go. Now, from the question, what volume of carbon dioxide gas is produced? So we are required to get something of carbon dioxide. So it means carbon dioxide is very relevant in this question. And then it's produced after burning 1.1 gram of what? Propane. So propane is still very important. So the other ones are not that relevant in this question. So we'll now bring them out. That's by isolation. So when we bring them out, it becomes C3H8. Then to give what? To give 3CO2. And remember, like I said, always we must represent the stoichiometric ratios in moles. This is 1 mole, this is 5 moles, then this is 3 moles, then this is 4 moles. All right. So while this one is still 1 mole, then this is what? 3 moles. All right. So we've been able to isolate. Then the next, we'll now convert, meaning we'll convert the language of the equation to the language of the question. So let's go. We are told to get volume. What volume of carbon dioxide gas is produced? So it means we need to convert this mole of carbon dioxide gas to what? To volume. And you can remember that I said that 1 mole of any gas occupies 22.4 dm cube of volume. So this is a gas. So 3 moles of it will now occupy what? 3 times 22.4 dm cube. Yes, because if 1 mole of this gas, of any gas, remember, occupies 22.4 dm cube, then this is a gas. So 1 mole of it will still occupy 22.4 dm cube. So 3 moles will now be 3 times 22.4 dm cube to get the volume that it will occupy. And when you do that, that becomes 3 times 22.4, that gives us 67.2. So 67.2 dm cube. We've been able to convert that. Then what language did they speak of the propane? Let's go. It's produced after burning 1.1 grams, meaning mass. So it's the language of propane is in mass, grams. So we have to convert 1 mole of propane to what? To grams. And by doing that, of course, you are aware that we have to sum up the relative atomic masses of each of them. And of course, in this case, carbon is 12 from the question, so it becomes 12 times 3, then plus hydrogen is 1, so that becomes 8 times 1. So 12 times 3 is 36 plus 8. And 36 plus 8 is 44. So 44 grams. So 44 grams would release 67.2 dm cube of CO2. Then the question, we have already converted now. We have converted the language of the equation to the language of the question. Then the last, we now ask ourselves the question, what volume of carbon dioxide gas? So X dm cube of carbon dioxide gas is produced after burning 1.1 grams, so 1.1 grams. So it means when you burn 44 grams of propane, you can get 67.2 dm cube of CO2 released. Then 1.1 gram, when you now burn it, how many CO2 in terms of volume will be released? So if this one releases this, then this one will release that, which is the unknown. So by cross multiplication, you'll be having 44 times x, then is equal to 1.1 times 67.2. And that becomes x equal to 1.1 times 67.2 over 44. So when we carry out the calculation, 1.1 times 67.2, and then we divide by 44. So that becomes 1 point. So our answer is 1.68 dm cube. So that becomes our answer. All right. So that's how you attempt questions on stoichiometry. Though we still have others I would not really seen. But then again, these ones can actually be eye-openers to understanding how you can calculate easily stoichiometry. All right. These are stoichiometry of reactions. We still have stoichiometry of solutions. We'll be looking at molarity, molality, and as well as even normality. Then we will not be working with chain formula. Of course, you must be acquainted with this chain formula. This is very, very important. Let me just quickly drop the chain formula so that in our next video, we can see the applications of this chain formula. So this formula is giving us number of moles is equal to mass over molar mass, then equal to number of particles, It could be atoms, molecules, or ions over 6.02 times 10 to the power of 23 Avogadro's number is equal to PV over RT, then is equal to CV over 1000 cm cube. All right. So these are actually things that you need to understand. Then we still have another one equal to V volume at STP over 22.4 dm cube. 22.4. So with this chain formula, you can attempt quite a number of questions from stoichiometry. So you can write down this chain formula to be of help to you in calculations involving stoichiometry. So it's my hope that you've been able to understand some certain stuffs about stoichiometry. All right. So don't forget to like the video, comment, share the video, invite your friends to this channel so that they get the very best from this channel. I wish you guys all the best. Thanks for watching and don't forget to subscribe. God bless.